Okay, so good morning, uh, physical science class. No, let us have a lecture today on reflection, refraction, and probably on some concepts that we will derive from light. No? So a beam of light, no? A light ray. No? What do we get out of it? No? So let's try to differentiate one or two of these terms and how do we see them in the real life context. No? So if there are actual phenomenons in the world, no? Then where do we see reflection, where do we see refraction, and so on. No? So light is very significant to us. No? So without light, no, we will not see any object at all. No? It is believed that objects emit light, no? Whether it's a light that they produce on their own, or it's a light that is reflected on them, or a beam of light that is striking them. And again, that light that comes from the object, again, allows us to see objects. So our eye, our sense of sight, will work with light and eventually allows us to get a picture or an image of an object. No? Now let's see some pictures here in front of us. We call this as either specular or diffuse reflection. No? So let's begin with the idea of reflection. So this is what? Specular or diffuse reflection. No? So you notice that the guy is seen in the mirror and he's very clear. No? So next one is the image seen here on water. Is it specular or is it diffuse? No? So again, this is not the actual tower or building. No? We see it simply, uh, we see it in water. So what do we call that? Specular or diffuse? Now here is half of the image maybe covered by some kind of this may be a picture of uh, a reflection of a certain image, but half of the image is rather blurred. No? So is it specular? Is it diffuse? No. So if it's specular, which part? Now, specular or diffuse. No. So here is another one. So the actual object is on top. No. So this is the mountain, and then below it is water, and then therefore we see a reflection of the mountain on the water. No? So what is this? Is this specular or is it diffuse? No? Now light again allows us not to work. No? Light works with our eye. It enters our pupil. You notice that our pupil, the pupil of our eye will respond to the amounts of light. So those are things that we actually use to be able to still recognize or to check whether somebody is still alive. If we pass a beam of light on the eye, and if its pupil dilates or shrinks, then therefore that person is still alive. So again, much of our vision is again using our eye, our sense of sight. So again, without light, we will not see anything. Now again, here's another image that we see below. This is again reflection. So reflection is when the wave of light strikes another surface, and therefore we see it bounce back, and probably it enters the eye of another person, and then therefore you see the image below this. So that's reflection. So in reflection, there are actually three lines that we consider. So we call this as the law of reflection. So the beam of light again strikes a surface. So this is an impenetrable probably surface, and this is the normal line. So this is perpendicular to the surface, and the red color is the reflected ray. So the blue one is incident. They call it as the incident ray or the incoming ray. And what one thing is that the angles that are formed with respect to the normal line, to this broken line, the angles formed by your incident ray and your reflected ray, they are always equal. No? So we call this as theta I, no? Or the incident angle, angle of incidence. And then on the other side is the reflected, maybe that's theta R, no? Small letter R. So that angle now is equal to the other angle here. No? So these three lines, according to this law, no, they are part of only one plane. No? So if it's a flat figure, then they all fall into that flat figure or that piece of paper. No? Again, that's the law of reflection. So if this is a surface, the angle formed, no, by the incident ray with the reflected ray are always equal. No? Okay, so law of reflection. No? So we cannot violate that principle. No? Now, again, in terms of the term specular or diffuse reflection, when the reflections no travel in several directions, then we call it as a diffuse reflection. No? The image usually there is not very clear, no? Blurred, no? And perhaps here the the reflected light, no? So there's a cloud above. No, you notice that its image is directly created below it. No, and again, no, the reflection there is happening no, on a very smooth surface. No, so the image here is known as specular reflection. It's very clear, no, just like in the mirror, no, and other surfaces. No? Now again, now that will happen when the surface is rather no, flat or smooth. No? But when the surface is very rugged or it's no, irregular, no, then the reflection will now travel in several directions. No? Now, some of these reflected rays will converge, no, or they will intersect with each other. No? And again, no, one description for diffuse reflection is that this may appear a little bit more brighter, no, because the light here sometimes, no, when they intersect each other, no, will produce a more intense reflection in terms of light. No? However, for the image, no, the image is rather kind of blurred. No? Now, for specular reflection, all the reflected lights are moving no, in parallel direction. No? So none of them are intersecting each other. So you'll see a rather no, clear image if it's a kind of an image and this one is a mirror. No? Now, this is an illustration, a very common no, illustration. When we dip pencil, we notice that the pencil is no longer straight. No? So the portion that is in air will have a different angle, and then the portion of the pencil that is in the water will be rather kind of bended. No? So there are two mediums here. No? One is water and the one above is air. No? Now you will only notice this when the pencil is dipped into two different mediums. No? Now we term this or we explain this as refraction of light, no? The bending of light. No? Again, one typical illustration there is that of no, submerging something in water. No? So this straw, no, of course, will appear bended, no? Will not appear straight. No? So again, this is happening when there are two different mediums that you are using. No? So the change in the medium allows the speed of light no, to change. No? So when that changes, then it seems now that there's now the bending of the actual object. No? Now, the shallowing effect of oceans or of swimming pool is also no, explained by refraction. No? So if a light no, passes from the bottom of the swimming pool and goes to your eye, no? If it will not travel straight, then therefore no, the bottom of the pool will also appear shallower. No? Or you may probably think that it's safe to swim. No? And supposing you don't know how to swim, you thought that you can stand on the pool, no, but you'll realize that it's very deep. So again, on the shallowing effect of the swimming pool with water, no, is described and explained by refraction. So refraction is a change in the speed of light. No? So because of the two different mediums, light will travel no, at different speeds. No? Now, the laws of reflection, or we call this as the Snell's law, no, is probably no explained this way. No? So if you beam a light no, directly in water, but you beam it no, perpendicular no, to the water, meaning you beam it directly downward, then light will not bend. No? However, if you will tilt the angle no, of the light here, then light will no longer travel straight. No? Now we see refraction occurring in the case of prism, no? Glass prisms. So you'll notice that when you strike a glass prism with light, then light will now bend in several directions, and you'll notice that color is now displayed no, on your glass prism. No? So you see seven different colors, as they say that there are they say now that there are seven colors in our refracted light in a glass prism. But actually, no, we only see now the visible ones, and we probably think that there are only seven, but there are actually an infinite number of light there, no? Colors of light, no? So maybe it runs in what millions, because again, the use and the variations or contrasting colors there are increasing, no? And again, no, if we try to identify it, no, we cannot only say that there are seven colors available there, no? But anyway, that's one, no? And when you also sprinkle water, no? When you water the plants, no, in your garden, you also see that there's this bubble of droplets of water that are spread in the air, and then you'll notice that if it is still no, there's still daylight there, the beam of light that strikes those bubbles of water will also create no a refraction of light, and you'll see something like a rainbow no, in the sprinkled water in your garden. No? So here's an illustration of our loss of refraction. So this incident light, no, the one that is seen above, no, maybe this is the air here above, and the one below is water. So there's an angle formed by your incident ray, no, with respect to this normal line. Again, this normal line, we call this normal because this is always perpendicular or 90 degrees with the surface. No? So the angle formed there no, is called as angle of incidence. The angle formed below now with this refracted ray is known as the angle of refraction. No? Now usually this angle above and below are no longer equal, no? Not like your angle of reflection. No? Now those angles, no, actually, no, this may bend nearer to the normal line when I think now the substance below is much more denser than the substance above. No? So if you have water, water is more dense than air. So this one will bend no, um, relatively no, away, I think away from the normal line. No? So those are changes in the speed of light, then therefore no, this light will no longer travel straight. No? Again, no, that law of refraction is described by this principle called Snell's law, no? Which it divides no, the two speeds of light and then call it as an index no, of refraction. So Snell's law shows the relationship between the angle of incidence and the angle of refraction. And then there's this equation no, where we can actually apply the Snell's law. No? So V1 and V2 here are the, no, these are the velocities no, of your light no, at two different, or waves no, at two different medium. No? So again, no, the if medium number two no, is more dense or it has a higher index of refraction than surface one, then the light or the beam no, of or the refraction of the wave will now be bended no, towards the normal line. No? Okay, so that's Snell's law. No? Now we will try to go to photons, and photons are another phenomenon no, in our study of light. No? So photons are believed to be no, the submicroscopic particles of light. No? And let's try to check no, who studied and look into the principles of these photons no, and why do they study it. No? Now, the first name probably that we will encounter no, in our study of the photons is the name of Isaac Newton. No? So now again, no, when we deal with light, we will also make mention of how fast light is traveling. No? We know light to be traveling at 300 million meters per second. No? And they believe that light travels no, at that constant rate. No? Especially if you let light travel no, in an empty vacuum in space, light will always not travel at that same speed. I think it's also explained by one guy, no, Albert Einstein, in his theory of special relativity. No, regardless of whatever no means no you let light travel into, light will always be traveling at a regular value of 300 million meters per second, or that's around 300,000 kilometers no per second. No? So just imagine how fast that is. No? Now, the very first persons who try to explain or try to measure no, the speed of light, no, one is Galileo. Probably, no, they get a value, but they did not really no, get the actual measured length because of the limitations of their time. No? The equipments that they're using no, are very, very crude. No? So maybe no, they tried to measure like one guy there is Romer. No? Before he knows it, light is already on the other end. No? Because again, no, they did not realize that it is traveling at such a very high speed. No? Again, one of the scientists who studied the speed of light is Galileo Galilei. No? He designed an experiment to measure the speed of light. Next is Ole Romer. No? So Romer, no, I think Romer invented some kind of a gadget. But one of the things that he observed no, is this moons of Jupiter, and one of the moon there is Io. Yeah? He was able to notice the maybe no made some trackings of the shadows no, of uh, the moon no, of Jupiter. No? And again, no, because of that, he was able to made an attempt no, to measure the speed of light. No? So again, no, he's the next guy, no? And another person who probably tried an attempt in measuring the speed of light. No? But we realize that light no, is part of a huge or a lengthy spectrum of wave. No? So we call them as the electromagnetic waves. No? Our light waves there is only a segment, a tiny segment of the electromagnetic wave. So the electromagnetic wave or the EM wave comes from the sun. No? So it consists of gamma rays no, and other harmful rays. And then on its far end, no, there's this radio waves that we use for transmitting our TV signal or radio signal. No? So we see that no, from the waves that comes from the sun. This wave does not need any air. It does not need any medium. We call that one as medium. It can propagate itself no, even in a space called a vacuum space. No? So it is a self-propagating wave, and then it's traveling at this value. You'll notice that this value, the 300 million meters per second, has been mentioned already to be the speed of light. No? And the the thing that we notice is that they have the same value because again, light is a part, no? A tiny part of this electromagnetic wave. So those radio waves, those gamma rays, no, somewhere in the middle, no, a very very short, no, portion of that spectrum is now our visible light. No, that's where we see our colors, no, the different colors that is noticeable to our eye. No, but again, no, that small spectrum is the one that is only uh, there is one that is sensed by our eye, no? Because that's the only available wavelength, no? Visible to our eye. No? But anyway, no? That's the speed of light. No? If we think of light as a particle, then we are considering it. No? We are considering the particles called photons. No? Isaac Newton was the first one no? Who thought of light no? As something like matter. No? You can have no particles of it. No? But probably no, they are kind of massless. No, they don't possess any mass, but they can be. No, if you think of particles, it's like some bits of objects like stones. No, which probably you can gather. No, so again, no, he formulated. No, Newton formulated the theory of the particles of light. No, now these submicroscopic particles he calls them as photons. No, now photons no are elementary particles of light, and they also have no properties like of a wave. No? So therefore they call light as dualistic. No? Light is both particle and it's also a wave. No? Okay, so some properties of light or photons. No? So they move at a constant value, 300 million meters per second. They are massless. No? They carry no energy and momentum. So may harapan sila builo, no? We call it. No? So if they hit on other particles, probably they can they can let that other particles no, move in a different direction no? Because they carry with them some kind of a momentum. No? Now, however, no, they are believed to be no, of no charge, no, similar to a neutron. No? So they are they are neutral substances. No, they have no charge in them. No? Now, this particle of light, no, however, no, could not explain no, that when several colors of light come together no, and strikes a surface, it cannot explain why light produce no, a certain other color. No? Or when white light, no, for example, strikes on the same surface, it cannot also no, explain why it becomes intense. No? So we call this as light interference. No? When varied colors of light no, come together, no, then what will be their effect? No? So again, no, for varied colors of light no, falling on an intense light, no, like two white light, and then there's another colored light that comes there. No, what will be the eventual color? No? So again, no, a new color is eventually produced. No? So it is explained by the phenomenon called no, light interference. Now, Albert Einstein tried to revive this theory of light no, because initially it cannot be explained by the resulting color, no, cannot be explained by the effect of uh, the theory, no, the theory of particles, no, or photons, no. So, um, in here, no, Einstein introduced no the idea of the photoelectric effect, no, and according to him, this photoelectric effect, no, um, when light probably strikes a surface, electrons, no, are emitted, no, from a metallic surface, no, when subjected to an incident light, no, consisting of photons, no. So when photon strikes a metallic surface, electrons are eventually created. No? So again, that phenomenon no, of that electrons uh, that are emitted from the surface no, became known as no, the photoelectric effect. Now, the atomic spectrum no, is the spectrum of frequencies of the electromagnetic radiation emitted or absorbed during the transitions of electrons no, between energy levels within an atom. No. Electrons that have absorbed energy no, jump to a higher energy level and are said to be in an excited state. No. So when we beam no, light no, on the surface, then the electrons there no, gets excited and they will now no, probably move in a rather different manner. No? So the excitation will increase no? Because it receives a higher form of energy. No? So again, these principles of photoelectric effect. No? So maybe no, that those principles now allows us to understand no, why there is such thing no, that we see no, in the interference of our wave. No? So we thank Isaac Newton for that principle. No? So these are the two topics, no, that we will try and have, no, for today's quiz. No? So try to review this one. No? And God bless, guys. No?